You've heard it all before. Global warming, the greenhouse effect, ocean acidification. They're all terms that we've come across time and time again. But if these really are problems to be dubbed the challenges of the century, then it's remarkable that the situation hasn't improved, but only worsened. Despite New Zealand being a world leader in environmental sustainability, under half our total energy consumption came from renewable sources in 2015. This means that most of the resources we are using to produce energy cannot be readily replaced by natural means on a level equal to its consumption. However, the main issue with the combustion of non-renewable energy sources is the release of carbon dioxide emissions into the atmosphere. Carbon dioxide is a greenhouse gas which accumulates in the greenhouse layer, trapping the sun's radiation and warming the earth. This has far-reaching effects from rising sea levels to changing global climate and disruption to ecosystems. The carbon dioxide also dissolves in water to produce carbonic acid, which acidifies our oceans and changes the locations that marine organisms can tolerate. It can also cause acid rain, which erodes buildings, harms animals, and damages forests. The scale of these negative impacts from the combustion of fuels is becoming a growing threat to New Zealand's pristine environment. So now we've established that we've got a big problem ahead. But the solution? Algae biofuel. Hey, I know what you're thinking. Along with corn fuel, tidal power, all those crazy other innovations, it's been done before, but is destined to be too costly in real life. Well, from today, that's about to change. But before we delve into the gist of the technology, let's answer the question, why algae? 3 reasons. Firstly, all algae photosynthesize, which means they can combine carbon dioxide and water to produce the sugars required for their life processes. This means that the combustion of algae biofuel is carbon neutral. Although carbon dioxide is released in the combustion of the biofuel, the same amount of carbon dioxide is absorbed as the algae grows, so there's no net effect on carbon dioxide emissions. Reason number 2 is that algae are very easy to grow, so they require very little attention and thrive in water with poor nutrition. Finally, algae have a high percentage mass of oil. Coupled with high growth rate of algae, this means that the oil yield per unit area for algae is significantly higher than for other biofuel crops. This is true to the extent that the oil yield per unit area for algae is over 15 times higher than the oil yield per unit area for oil palm, which is a biofuel crop with the next highest oil yield per unit area. Okay, time for a reality check. As it stands, producing biofuel using algae is not very widespread due to the high cost of growing algae. Existing methods involve growing algae in ponds, where nutrients can be supplied and algae can be harvested using sieve-like technology. To make this technology feasible for New Zealand, we would have to play to our strengths, and considering that our country is surrounded by water, it kind of makes sense to find a way to grow and harvest algae in the ocean. Currently, this has not been done, because A, it's hard to keep the algae in one area where it can be collected, and B, existing structures do not provide enough surface area to make growing algae cost efficient. So what we need is a design that has a large surface area. But we can't just put a large flexible mat in the middle of the ocean, since the action of the waves will quickly tangle it, reducing the surface area. On the other end of the spectrum, many small mats wouldn't work either, because it would take far too long to collect each individual mat in. Okay, what if we made our surface a large rigid sheet? Well, the problem with that is that waves on a rigid surface quickly cause breakages. And that's not even considering the question, how are you going to take a big rigid surface in? So the design we need not only has to be flexible enough not to be broken, but it also has to be rigid enough not to get tangled. Enter Miura Ori, a method of folding a flat surface into a smaller area. It's essentially a Japanese origami fold. Similar to seed mats, these surfaces could be embedded with the nutrients required for algae to grow. They could then be fixed to a suitable location in the ocean and left for the algae to mature. Since this technology has the potential to revolutionise the process of growing algae, I'm going to spend a little time today elaborating on how it creates this massive cost reduction through its high efficiency. The Miura Ori fold is unique in the sense that it's flexible but also unable to be tangled. This is especially crucial for placing such a structure in the ocean, where the waves will obviously cause it to move substantially. The flexibility of the structure means that it can move in phase with the waves so that the structure itself will be under less tension. This mitigates the potential for large waves to cause breakages, ensuring that the structure can remain intact for at least a 20-year lifetime. Another issue with traditional surfaces is that they're hard to take in and transport to a processing facility. As you can see, the Miura Ori fold has the ability to compress from a large and relatively flat surface into a compact and small volume. The surface is also very easy to take in because when you compress the fold in one direction, it automatically squashes the other. This compact volume means that more algae can be transported using the given resources, reducing transportation costs and making the technology viable for New Zealand. The third and final aspect of the fold that improves its efficiency is its large surface area that arises due to all the folds. This is desirable because more algae can be grown per unit area, so that the average cost of producing each litre of algae biofuel will be reduced. The surface of the structure will be made relatively rough. This serves a dual purpose. A rough structure has a greater surface area than a smooth structure, so greater volumes of algae can be grown on the same structure. This is analogous to villi, small finger-like projections that increase the surface area of the small intestine. A rough structure also allows algae to remain more firmly attached to the structure so that they're less likely to be washed off by strong waves. This increases algae yield, again maximising the efficiency of the growing process. Now that I've explained the advantages of the folding system, let's see what happens next. Once the algae have matured, the structure could be folded up and transferred to a processing facility where the algae are collected. This is made really easy by the Miura Ori fold because the algae can be removed just by compressing the structure. A new surface could immediately be placed in the ocean, allowing the growing cycle to repeat with optimal efficiency. It's important to note that these folds can be reused over and over again. Once the algae have been collected from the fold can be put back out into the ocean. Next, the oils need to be extracted. It's kind of like squeezing juice from an orange with the additional chemical reaction afterwards. Just through compressing the algae, up to 75% of the oils can be extracted. The remaining algae pulp can be mixed with cyclohexane, where the oil from the pulp will dissolve in cyclohexane, allowing all that pulpy stuff to be filtered out from the mixture. The oil and cyclohexane can then be separated by distillation, as they have differing boiling points. And voila, your biofuel is ready to go. Now, to bring this idea into reality, where would these surfaces be placed? Picture Whanganui, a town on the west coast of the North Island that consistently sets national records for high unemployment, high levels of poverty, and low economic growth. Factories that once contributed to the booming manufacturing industry lay disused and crumble. If this technology were to be introduced to Whanganui, it would in a stroke provide a source of affordable and reliable fuel, and a source of employment and development for the struggling township. All of the town's energy needs could be met with an area of 2 by 2 kilometres, which is readily available offshore. The existing industrial facilities could be converted at small cost to process the flow of fuel. The startup cost of the town would be relatively low, as what we're essentially doing is using nature's ability to harness energy from the sun. Whanganui would be able to draw on her own natural resources to provide affordably for her people. But Whanganui is not an isolated case. Gisborne, Greymouth, Westport, New Plymouth, they're all ideal coastal locations. The lack of dependence on weather, the low initial cost, and the ease of transport of the fuels means that it really is both a versatile and economically viable opportunity. By now, it shouldn't really be a surprise when I say that this technology has the potential to deliver significant economic, environmental, and social benefits to New Zealand. In the future, the price of petrol and other fossil fuels is expected to skyrocket as existing stores dwindle. If we can obtain a large proportion of our energy from algae biofuel, this will act as a buffer against rising oil prices, allowing our economy to remain competitive in the global market. We'll be less reliant on importing fuel from other countries and could potentially even export this technology. This will boost employment in towns like Whanganui and help combat the alarmingly high rates of poverty. In terms of environmental benefits, the carbon neutrality of algae biofuel ensures that we as a country play our part in stopping global warming and the adverse environmental effects associated with it, rising sea levels, ocean acidification, and acid rain. The recreational fishing industry alone is worth $1.7 billion to the New Zealand economy, so it's clear that environmental health and economic health go hand in hand. New Zealand calls for a safe future safe from rising sea levels, a future safe from poverty, and a future where social communities enjoy independence and growth. Such a great future does not have to come at great cost. Algae biofuel provides us with a viable, affordable promise of well-being. Algae is a clean future. Algae is a green future. And algae can be our future. Thank you.
Thank you, Andrew.
Thanks, Andrew. What's cyclohexane?
Cyclohexane is a hydrocarbon, and before you ask, it is poisonous, it can damage the environment. But the use in this technology is that it's stored in a compressed cylinder, and it can be reused over and over again. Once the oil and cyclohexane can be separated, the cyclohexane can be reused in another cycle, so it's never released to the environment.
Right, so you think it's still sustainable?
Yes, because what you're doing is you're using some of it, but you're just using the same amount indefinitely.
Your figures, something like 9 million litres per square kilometre
Per year.
of oil versus not much at all for corn, for example.
Yes.
Really?
Yes, really.
How come? How come that's so much more? Is it because you can have a whole cube kilometre rather than just a flat kilometre?
Partially with that, it's because obviously with corn...
But you're not having a cube kilometre, are you? It's only the surface of the ocean.
It is, but with corn, it goes straight up, but there's only a small amount that you can actually use for the fuel. Algae, pretty much all of it can be used. But another benefit of algae is that it photosynthesizes really efficiently. Like, as you've noticed, it's green. It's very efficient at photosynthesizing, so there's a high yield of glucose as well.
Is there an environmental impact of covering a, what did you say, a 2 square kilometre block of ocean with this stuff?
So for towns like Whanganui, the coastline isn't really used anyway. You could put these maps... You could put these mats a few kilometres offshore and they can stay there. Okay. It's not used anyway. We can have a channel where, let's say, ships can move and not pass it. So it's totally fine for the coastline.
What's this fold material made of, Andrew?
This material can be made of biodegradable starch polymer. Think of it as having similar properties with plastic, except that you don't need to use the oil in producing the plastic. Starch is manufactured naturally by plants in their processes. So basically they usually produce glucose, all the excess is converted to starch.
But if it's biodegradable, then you can't reuse it as you suggested, can you?
So you can actually control how long it takes to biodegrade. So as I mentioned in the speech, the lifetime of the fold is 20 years. So let's say in this lifetime, if it does manage to detach an extreme weather event, because it's so close to the coastline, it can be easily collected back in. But after 20 years, the starch will naturally biodegrade. That's like the maximum lifespan it has.
Thank you.
Thank you.